Right, so hello everyone, hope you can all hear me. There's always problems with these systems, so if someone could just type something to say yes they can hear me, that would be great as usual. Hooray! So one day everyone's going to keep quiet and I'm going to think you can't hear me. Anyway, right, so at the end of last session we started looking at analog gain control and introduced this interesting idea of how should we say this, that we can control an AC parameter by controlling a DC parameter. So in this case we controlled the gain of this system by controlling the value of this current here. So this is a DC parameter, it's a fixed value, but we can change the gain by varying this, and this is something that we will look at going forward again as well. So let me just get rid of me in there. So that was a recap of what we very quickly looked at the end of the last session. And we looked at some of the equations involving that and noted that we were going to have a current mirror down here which we then control with an input voltage which controlled this value of this current, which was mirrored, which would control the overall gain of this because it changes the GM, the transconductance of this particular transistor, which remember is based, the value of GM is related fundamentally to the bias current in the tail of this thing. So the current going through here dictates, for no signal going in, that dictates what the value of GM actually is, and that is dictated by the value of this current in this current source here. So we can control the value of IC, this one here, which gives us a new value of GM by controlling the value of this current in here, which we can now control by just changing this voltage here. So that's quite nifty little thing to do. So, and this allowed us to build this thing called a two-quadrant multiplier. So by varying this voltage here we can vary the gain of this system here, and in this case you can see we can do amplitude modulation of a carrier with a low frequency signal which manifests itself in the envelope. So this is an easy way of making an analog multiplier or an analog amplitude modulator, but fundamentally we're just changing the gain of the circuit. And this is where we got to at the end of last week. The interesting part about this is, so that's a voltage controlled amplifier that we've looked at. The same kind of idea can be used to make a voltage controlled filter. So we just introduced this, we haven't done filters properly yet, that comes in a week or so. But the idea is straightforward enough. You've got a good idea of what a filter is anyway. So in the early days of analog music synthesizers, and this is an original music synthesizer, great big thing with lots of controls and knobs and wires to plug in, very complicated things in principle but actually quite simple in practice as well. Mr. Moog, who developed the first synthesizers and then moved on to look at pressure valves and things, developed a voltage control filter based on a ladder structure. Ladder structures are quite interesting and easy to work with. So we're going to look at the original famous Moog filter, which is a fourth order Butterworth type low pass filter, and to change the cutoff frequency of this filter, to change the point at which it has an effect, the GM of the structure is varied. So this again, we're controlling GM by changing a bias current, and this is going to control the cutoff frequency of a filter. So we're controlling this sort of AC parameter with a DC response, which is quite a neat trick really. So what we're going to see is what happens when the bias current in the system is varied from 50 microamps to 700 microamps, and as the current increases the cutoff frequency will also increase, as we shall see hopefully. So it looks complicated. This is an LT Spice simulation of a fourth order filter, but you can start to see parts of this circuit that you maybe recognise. So you recognise the current source, and you'd recognise a sort of a long tail pair type structure. So we've got this differential cascade, if there's only one transistor here and one transistor here, you'd be relatively happy with what it was. And all we've done is cascade 4 of these, or 5 of these things. So one is the amplifier, and then these are the frequency control elements. And what's happened is we've just connected a capacitor across the outputs of these 2 transistors, which gives us a sort of a phase difference in the outputs between these 2. So we're building a sort of an RC time constant in. So it's very clever. It's not easy to understand, but we can model it. So we've just put some bias steps in here, and then our signal comes in here. So most of this is all biasing. With transistor circuits, everything is bias. That's the important thing. So we build this kind of structure and you model it, and then you can see that as we are changing the bias current down here, the values of I, the frequency response, which is normalized here, starts to change. So this is the linear response, and you can see the cutoff frequency is around about here. For this particular bias current, it's around about 15 kilohertz, and as you increase the bias current, the cutoff frequency drops right down. So that's what it looks like in linear terms. If you plot that as a log-log curve, or Bode plot, or whatever you want to call it, you can start to see, you get the flat responses, and you can start to see where we would 3 dBs where we'd have our cutoff frequencies. So you can see the cutoff frequency is quite smoothly controlled, and we've got a nice flat response in the pass band, and it's controlled by just varying this tail current down here. So it's quite a flexible sort of system. It looks horrific. But what happens in the old analog synthesizers is they use this to filter dynamically a harmonic rich signal, such as a square wave. So if you remember your Fourier analysis or Gibbs theorem for square waves, you'll know that there are lots of harmonics in a square wave of a fixed frequency. And if you listen to a square wave being played through an amplifier, it makes a very harsh noise. And then if you filter it and start to filter off the harmonics by putting a filter on it, you can get a smooth sound. Eventually it's just the fundamental, which if you just filter everything else out and left with the fundamental, you're left with a sine wave. So you can hear what a sine wave sounds like. It's quite smooth and gentle. And you can hear what a square wave sounds like, and that is quite harsh and grating because there's some high frequency components, and this filter allows you to move between them, and you can do that imaginatively at high speed, at low speed, or how we go. So this developed itself into something called the synthesizer, and here's the architecture of a typical analog synthesizer. So it's used for music, but this architecture is used for all kinds of other things as well. And we end up with a voltage controlled oscillator, and we'll talk about those, or Kay Lee will talk about voltage controlled oscillators further on in the course, but it's an oscillator that changes its frequency depending on the control voltage. So again, a DC input changes an AC parameter, and this is obviously for a synthesizer is for generating notes. We then have a voltage controlled filter, which we've just looked at, which will then filter those notes, and if they've got harmonics in them, and usually a sawtooth is used in an analog synthesizer, you can filter that out and make some very interesting noises. Then gets amplified with a volume knob using a digital gain control or a voltage controlled amplifier in a lot of cases. And then there's, in this case, there's also built in something called an LFO, which is a low frequency oscillator, which is actually then used. You can see that this low frequency oscillator can be used as an input to the voltage control filter, which allows us to change the feel of a note dynamically as we go along, and keyboard or whatever. So that's what we've got here, a little keyboard here. Now what I'm going to try and do is I'll have to share my screen rather than the camera, otherwise you won't be able to hear it. So if I share the screen 1, share audio, share. Okay, so with any luck you should not really notice very much difference. The difference being that when I play this video, you'll hear it, I hope. Let me just see if it'll play. So I hope you can hear this. Stopped. You can if it plays. Right, okay. So this is someone just playing with an oscillator and a voltage controlled filter. So he's twiddling the voltage controlled filter knob at the moment to get some noises out of it, and you can sort of see the sort of noise we get. And then, in a style favoured by the likes of Ed Sheeran, we're going to stitch these things together, and hopefully we can get an interesting sound out, which is just made up of single notes being filtered and changed dynamically. We'll let it run for a couple of minutes until we get bored. Right, so enough of that. But that is all achieved by just using this structure. So it's a single oscillator which we can control the pitch of with the keys. It's a voltage controlled filter, so we're showing the changing the harmonics of the signal that's coming out dynamically at different rates, as seen by the twiddling of the knobs. So we've got two knobs for the VCF down here, and then driving that through a low frequency oscillator. And with a bit of imagination, you can see you can get a long way. And so back when synthesizers were in vogue, first time round anyway, in the 80s, this was very standard and state of the art at its time. There was a resurrection recently, a few years ago, and it's now been squashed into a small thing, and people can use that. And now that's all software enabled. Anyway, we hope that was interesting. So the transfer function of that system can be shown to be, well, not that system, but the filter itself that we just looked at, the Moog filter, is just this. It's a fourth order filter. Let's go back to a pointer. Fourth order filter, power of 4 here. S is obviously the Laplace operator, so there's j omega hidden in there, and this is the coefficient of S, which effectively dictates the cutoff frequency of the system. And you can see the value C comes into play, which is fixed. Vt is constant within the system, and IF is the tail current, which we can vary. So we can vary the cutoff frequency of this system by changing this DC current in the system. That's just a sort of a standard little trick that people have used for many years, and that was the original one that was done with transistors. So the same kind of idea is quite easy to do these days using something called an operational transconductance amplifier, or OTA, which is like an op amp. We'll have a look at it in a minute. It takes a differential voltage input but has a current output. It also has a bias current input because it's got a current output. And this is the bias current input is the interesting thing that we can start to play with. We usually follow the current stage by a current to voltage converter, and that's usually an op-amp because people like to have voltages out. So this is something that might be done to create a single order, first order filter type structure using an OTA and an op-amp. So you can see this is the operational transconductance amplifier. So it's got a differential input like an op-amp, it's got a triangle like an op-amp, and then it's got this current source as the output and another input here, which is the bias current. So you can show that we can actually change the bias currents of this stage in here. So it's an integrated form of the sort of thing we looked at just now. And in this case, if you want a frequency response, you follow that by, in this case, a current to voltage converter, but with an integrated stage in there as well, because we want to introduce a capacitance for a filter. If you didn't want the filter response, you just wanted an amplifier, you just change this capacitor for a resistor to make a transconductance amplifier to turn the current back into a voltage. So this is just another way of sort of changing the gain of this system. You just change the current going in here. So a typical example of an OTA will be the TI LM13700, which you buy in a pack of 2. And that also includes a voltage buffer in there with these pins available for you to connect components of your choice for whatever function you want to generate. So to analyze these kind of things, the output current is the interesting thing that we get here. And so I/O, the output current of this, is defined the same as for an op-amp. It's some gain term, in this case GM, multiplied by the difference in the voltage of the two inputs. So here's the two inputs. We want the difference in the voltage of these two inputs, and that's multiplied by some factor in the op-amp to give us an output feature. And in this case, because the output is a current, it's a transconductance, and we define that as GM. Okay, so GM is dictated by the amplifier and can be changed by adjusting this current here, this voltage here rather. So in the case above, because one of the terminals is connected to ground, the output current is equal to GM times whatever voltage is appearing at VOTA plus. So it's just a standard op-amp type analysis. Let's hide that. And if everyone's interested, there's a link to OTAs. They're not common, but they're quite interesting and can be useful in certain situations. And then if you wanted to, you could analyze this using standard node analysis and the standard analysis for op-amps. So we'll just look at, say, what's going on at VOTA here. We call this the VOTA. And so we would just work out what's going on by doing a nodal analysis for these components here of what's going on here. So we're just saying I in, I out is equal to these things. So we've got V in divided by V in minus the voltage at this point divided by that resistor. That tells you what the current is there. The current here is going to be the difference in voltage across here. So we've got the current coming through here. V out minus VOTA divided by 10k again. And then we've got 220 times IR going here as well. Do a standard nodal analysis on that, and you end up with the voltage OTA is given by approximately V in plus V out over 47.45 in this case for those values of components that we've got in there. Next we calculate V out as the current, as the voltage across the capacitor, because one end of this is grounded and we've got a virtual ground here. So this voltage point is at 0, and therefore we can work out the current through here very straightforwardly. So I output current, which is the output from this thing here, is then just GM times VOTA, and from that you can rearrange that to get a transfer function. So it's a fairly standard analysis, not much going on. We just apply the rules that we learned in the first year for nodal analysis. Don't get panicked by it. Rearrange everything to get a transfer function, and we end up with a transfer function that looks like -1 over some coefficient of s plus 1, which we would recognize as a single pole function. And the value of this, the cutoff frequency of this pole is given in this particular instance by 47.45 times C, whatever value of C was, capacitance, divided by GM, which we've got control over. So if we just go back and have a look, so we've got this value of C dictates what's going on. The various values of resistance in here will combine together in this transfer equation to give us 47.45, and then this current going into here, the bias current going into here, is the thing that dictates the overall frequency response. So that's what we've got here. Transfer function is related to S equals j omega, some constant dictated by the components in the circuit, and GM we have control over by changing the bias current. So that allows us to then create an OTA, operational transconductance amplifier implementation of the Moog filter without having to worry too much about individual transistors. It's more an integrated thing and looks a bit like an op-amp. But again, the key point here is the control of the AC performance of this system. Its frequency response is controlled by a DC parameter, which in this case is just the bias current, which is just something we have control over at that point. So just to complete what we need to do to make an interesting filter like that, that's a first order filter. We'd have to cascade 4 of those together to make a 4th order system. You'd have to do some more complicated maths and balance things to get a proper filter response, but in the case of a music device like the one we've just heard, people tend to be not that interested in the absolute mathematical response. They're interested in making interesting noises. So there's no Q control or damping factor response in there. We have to add some feedback around our filter core, and that gives us a response then that looks like this. Once we add some feedback around, and we change this value of K, we get interesting responses. So in this case, if you simulate that 4th order transconductance amplifier, so 4 of those stages we just looked at, with a bit of resistance or a bit of feedback around the outside of it, you can see that with different values, K running from 0 to 3, we get responses where we're introducing the little peaks. And remember, with the operational or the transconductance amplifier we looked at earlier, we were trying to get rid of the peaks and flatten it down. In the case of a music system, you're actually quite interested in peaks, because that emphasizes certain frequencies and makes interesting noises, as you've just heard. So what we're trying to do there is it says here, it's color the resulting spectrum, which means sort of emphasize certain points over other points and just make it sound interesting. But mathematically, it's not an easy thing to analyze particularly. But the principle holds true. If we make K something interesting, we could make a fully controlled system with controlled cutoff frequencies and designed to whatever performance we're actually interested in. And we might see an application of that when we start to look at filters, particularly the Tau-Thomas structure, a bit later, in about a week or so. Right. So that was a sort of an interesting deviation away from to show how some of these systems can be used in hopefully an interesting way. We need to revisit charge amplifiers now, because this leads us on to another case study, which then leads us on to the technique of how to help us do the coursework. So it's a useful exercise to go. So as we know, charge amplifiers, they amplify charge, and they turn they don't turn the charge into, but they give an output voltage in proportion to the input charge going in. So they are a charge to voltage converter system. And there are lots of systems that generate charge, piezoelectric devices, which are used a lot in pressure sensors and microphones as well. And modelling these is an interesting thing to do. And it's not something that's normally covered in university courses in my experience either, and there's quite a lot of misinformation out there on the web as well. So it's worth just having a look at it, because it's not that hard, but people seem to shy away from it. So we need a model for a piezoelectric type sensor or charge generating sensor, and a model would simply normally be a capacitor in parallel with a current generator, where the current is proportional to the differential of the required charge, because remember, current is just a moving charge, so that there's mathematical links between them. So physically, this is what it might look like. I'll say physically, this in model terms, this is what it might look like. We've got a capacitor and a charge generating current source, or a current source that's modelling our charge generator. And so if we define the current source has to be a current, and we know that in terms of charge, I equals dq by dt, rate of change of charge with time, is a current. So we've set the value of this current source to be dq by dt. The reason we're not putting a charge source here is because most simulated, well in fact all simulated systems can't simulate charge sources directly. They can only simulate current sources and voltage sources, so we have to emulate a charge source with a current source, or a voltage source indeed. So that's what's going. So current is easiest to understand as current is a moving charge, and we take the fundamental equations q equals it, therefore dq equals I dt, and therefore dq over dt equals I. So if we make our current source equal to dq by dt, whatever, and q is the thing we're interested in, we've got the basis of a model. So we can model the piezo as a current source in parallel capacitor with a current source that has the value dq by dt. And if we remember that d by dt is equal to s, the Laplace term, then I equals sq is how we can define that from here. So it's a simple model, and in practice there'll be other things involved as well, but it's something we can work with. And if this was actually modelling a piezoelectric crystal, we would have to take into account all kinds of dynamics of the crystal as well. So in reality, Q, which is the charge being generated, we can replace by a function related to Q that defines the dynamics of the system. So that's something we can do, but we're not going to do it at the moment. If we like to deal with voltage sources, we can actually Thevenize this. So we can take this model of our charge generator circuit, our piezoelectric sensor, and we can Thevenize it and turn it into a voltage source in in series with a capacitance as well. And then it's just a question of what is the value of V in here to make this circuit equivalent to that circuit in terms of modeling. And again, standard approach for two-port networks. You look at the open circuit voltage, and that tells you what V will be, and if you look at the open circuit voltage, you can see that VOC is going to equal to SQ over 1 over SCS, which is going to be Q over CS. So if we make the voltage source equal to Q over CS and keep CS as the same, these are the equivalent of each other when it comes to modelling. Right, so they're equivalent, those two, as long as we keep our definitions the same. We've just applied Thevenin's transformation, and we end up with two models that we can now use in simulators. So it's easier to use the voltage source model for simulation, but I would say it's more intuitive to see what's going on with the current source model, particularly if you've got an understanding of how piezoelectric sensors work. Piezo coming from the Greek meaning pressure, electricity. So a piezo source, you squash it and it generates a charge. So you can sort of imagine squashing this and getting a charge to move. Not so easy to visualize with this, but they are equivalent. So we've already seen that a current source, which is fundamentally what we've got now, can be fed directly into an op-amp with a resistor in the feedback loop, and we can get a perfect current to voltage converter. We can do the same with the charge source, but this time we just put a capacitor in the feedback loop instead of a resistor, and we touched upon that last week. And so by looking at the virtual earth at the inputs, because there's a virtual earth here, because this op-amp is operating in linear feedback mode, we can see that Vout output over here is going to be equal to SQ over 1 over SCF, which is going to be Q over CF with a minus sign because it's an inverting amplifier. And this shows that the output voltage is independent of CS. So Vout, output voltage, is equal to the charge that we're interested in and a scale factor. Okay, so I've just been cut off. We'll wait for that to come back on again. Right. Am I back? Hopefully I'm back. Yes, okay. Good. Sorry, dropped out there. Hopefully I wasn't waffling on for too long before it went off. But the recording that I'm making will be me talking anyway, so when I upload that, that'll be complete. With just me noticing that I've dropped out eventually. Okay, so we've got output voltage here coming out of here related to the input charge, which is what we're interested in, charge to voltage, and it's related by a fixed value which is 1 over the feedback capacitance. And CS, this capacitance here, does not appear in this equation, which is great, because, and looking at it, it's intuitive because we can see there's a virtual ground here, and this capacitance is across that virtual ground, so there's no voltage across this capacitor, so there's no reason to think it will appear in the circuit as long as this virtual ground exists. In other words, there's a high gain in this amplifier. Right, so we've talked about bias currents. We need to introduce a resistor to allow bias currents, because otherwise there's no mechanism really for getting a direct current in, because remember, this is a differential. This current is related to the rate of change of charge, so we can't assume that there's the availability of a constant current in here, because this is just a model of our system. So we need to have a resistor here, and that introduces this low frequency response here, and gives us a cutoff frequency of RF CF. So this combination here dictates the cutoff frequency at this point here. So if we want this frequency response to extend downwards, we need to make RF CF the values according, which tends to mean making RF very, very big. If we use the voltage model, so instead of having the current source and the parallel capacitance, we just swap in the voltage source and the series capacitance and look at that. We can start to see maybe where this works, and you can work out the same equations. So if we look at this and we say, well, actually this is pretty similar looking to a standard op-amp inverting amplifier. So we could take this impedance here, this combination of impedance, call it ZF, and this impedance here, call it Zin, and do ZF over Zin, and that will tell us what the voltage response to this amplifier is, and it comes to CS over CF. And you say, well, hang on a minute, CS is appearing in this, and in the last one it didn't. They must be different. But actually, if we then swap, remember this is a V out over V in relationship, and then we say, well, hang on a minute, V in is actually defined as being V, which is Q over CS. So if we make the substitution for V in equals Q over CS in this equation, we find that V out then becomes CS over CF multiplied by V in, which is Q over CS, which becomes Q over CF, which is the same as we had before. And I apologise for mixing up big Q's and little Q's. They're the same. Right, so the difference is that it's easier to simulate with a voltage source than a charge source, as V is proportional to Q. In the case of the current source that we just looked at, the charge is proportional to SQ, so the current source has to be compensated for this differential function that's in there. But you can do it. So how do we simulate this? So this is all a long-winded way of introducing a SPICE component called a behavioural source. So this is a sort of a programmable source that you can put into SPICE, which can be programmed to give an output modified by a function. So you can just introduce mathematical equations into SPICE, and it will solve them for you if you want. But it says here, sadly, for reasons I don't understand, it's not permitted to use a current as a modifying variable, so you have to do it by using a voltage source as your input charge variable. So the reason, or what this means, will become apparent in a minute. So we can emulate or feed a signal into our behavioural source either using a voltage source directly, or we can use a current source and feed it through a 1 ohm resistor to give a voltage. In either case, we'll look at what that really means in a minute. You use the voltage as the driving function for the behavioural source and set up the behavioural source to differentiate this input. So we set up the voltage source as being our charge, or our proxy for charge, and then we can introduce it. Okay, so enough waffling. What do we mean? So what we can do is create effectively a sort of a pseudo charge generator in SPICE. So in this case we can have a current source here which is the equivalent of our charge. We put that through a resistor and that generates a voltage. That's what we're interested in. Or we can just generate a voltage here. And these voltages, either of these, are then used as the driving function for this thing, which is our behavioral source. So in this case we're saying that I, this is a current source, the current is defined by d by dt of the voltage at this node. So we can put whatever function we like in this box. So in this case we've said, let's call it d by dt of some other voltage. So if we say it's this voltage here, we're then doing the d by dt of that, and that gives us our S term. So we are now simulating a charge source directly in here by generating a voltage here and differentiating it. So this is the use of a behavioral source where the behavior is defined by other parts, other functions coming in. We could have typed just a function straight in this box here if we wanted to. They're very powerful and very useful. And if we wanted to simulate our voltage source model, we can create the voltage source model here, and then we define the value V here as being the voltage of our charge source emulator divided by whatever the value of this capacitance is, which goes back to the equations that we just generated. So I would suggest that if you're interested in charge amplifiers, that you just spend a bit of time going through the previous few slides and seeing where the logic lies, and maybe even creating a circuit with a behavioral source just to see how they work. They're very, very powerful things indeed. But this allows you to simulate this charge amplifier with standard voltage and current sources. That's the whole point of this exercise, so that we actually see what's going on. And then we simulate it, and we can see that we're getting this kind of response, which is what we sort of expected. So a low frequency cutoff. In this case, it's about a hertz or so is the cutoff, and then a flat response. And it's the ratio of the two, or the ratio of this feedback capacitor is the gain factor, if you like. It's not a real gain because it's a charge to voltage conversion rather than a voltage to voltage. Okay, and cutoff frequency is 1.59 Hertz as expected from R times C. So that allows us to simulate these circuits. And then you can start to see what happens when you play with the feedback capacitances on these things. So by running a nested simulation within SPICE, you can just see that we can change the overall gain and the cutoff frequency by changing the feedback capacitor, all these values here. But look, it's always following the same kind of response. It's just peeling off at different points depending on the value of capacitance that we've done. So if you want a wider bandwidth, then you have to accept a lower gain function. That all works quite nicely. Very nice. So simulated it with a 741 op amp just because they're easy to get out of the box, and the performance, we will notice, falls away with frequency. And at 1 megahertz we're starting to see, so we only looked at the low frequency response because that's what we've just been looked at. But if we look at the high end, we can see that at a certain frequency, about a megahertz or so, something interesting starts to happen, and we get the idea by now that this is probably due to the op amp gain falling away, running out of phase and gain margin, and starting to get to a point where the gain of the system is only about 1 or so, and therefore the virtual ground is starting to fail, and interesting effects start to come into play. So one way around this, it's a good idea to try and limit the gain at high frequencies. And this can be done by introducing a resistor on the input side as well. So it's just a simple knowledge of RCs and what they do. And this makes the circuit look like an integrator at high frequencies, so it's like a low pass filter. So what we're trying to do is have a nice flat response here, and then before it gets to this exciting bit where this thing's stopping working really, is we'll roll the gain off like this, so that we're just interested in this flat response. And how we roll it off is we introduce a series resistance in the input. Like this. So what we've now done is introduced a resistor here on the input side, and we've made a sort of an RC time constant here, and all of a sudden now we've now got control over the top end of this response. So this is the frequency range of interest that we've designed for, and it's nice and flat there, has a nice high gain in that point there. So you can see with a bit of knowledge that we can start to influence the overall frequency response and design for whatever we need going forward. So So it's possible to control both ends of the frequency response. You could, if you wanted to, just add a low pass filter to the output of the charge amplifier if you wanted to, which allows you to then add some extra gain in if you wanted to as well. So if we change the input resistance here, just to show what goes on, you can see that we can control the top end of the frequency response by varying that resistance, and we don't affect the low end. So the low end is controlled by the feedback time constant. The high end is controlled by the input time constant. But this should also tell us that any resistance in the cable connecting the sensor to the amplifier will affect the high frequency response. So we have to take that into account as well, because although we've introduced some resistance here deliberately to control the response, there may be occasions where we don't introduce that, but we get it anyway because the cable has some resistance. So this will limit the length of cables for these type of systems. Right, how are we doing for time? A few minutes. Alright, so we'll start this as an example, a capacitance example. So just to introduce the problem, one of my first jobs in industry was to I was working with a petrol pump company, and they wanted to come up with a system for measuring how much air there was in the fuel that was going into the petrol tank, because you want to be buying fuel, you don't want to be buying air, and fuel, particularly diesel, gets very frothy if you're not careful, particularly if the tank's getting empty. So they said, can you come up with a technique for measuring how much air is in the fuel that's going in down the petrol pipe into the car, because if it's above a certain value we get fined by customs people, so we want to know when it's happening. So can you come up with one that doesn't cost much, is easy to operate, and will solve our problem for us. Right, so the problem, and this is an interesting one to go through, because this is sort of defining how you would approach the problem of the coursework, which is to design a system not for air and fuel, but for building a radar system. So again, you've got to define your problem and put some limits on it to see what's going on. So as I said, there's capacitance. We don't want to be buying air instead of fuel, so we need a sensor, and then the clue here is we're going to use a capacitance sensor. This sensor operates by allowing fuel to pass between its parallel plates. So if you imagine it's a parallel plate capacitor in the fuel pipe, and the fuel is whizzing through it. So the fuel acts as a dielectric in the capacitor, so that will give it a certain value of capacitance. This is compared against another identical capacitor, except that this capacitor uses as its dielectric a sample of the fuel guaranteed to have no air in it. So it's like a sort of a reference. So it has exactly the same dielectric quantities as the pumped fuel, including variations due to temperature, grade of fuel, etc., which is a common mode signal, so a differential signal will be good here. And then when you get air going up the pipe, it only appears in one of these capacitors, and that will change the dielectric constant and therefore the capacitance. So the problem really boils down to measuring the difference between two capacitors, one which is relatively fixed and one which you hope is fixed, because it'll have fuel in it, but if it has air in it, it'll be very different. And so really, we're looking at two capacitances. We need to measure what's going on. So if we draw that as a little circuit, our fundamental sensing problem becomes, here's our reference capacitor, here's our reference capacitor, and here's our sensing capacitor, which would have the fuel flowing through it, and if there was air, the value of this capacitance would change. This one's always got guaranteed fuel in it. That itself is a bit of a problem to define, but let's assume we've cracked that one, so we've got a little sample of fuel in here. And then if we measure the difference in capacitance between these two, we can work out what's going on. So again, it's a differential signal. Any change in temperature affects these equally, becomes a common mode signal. And we need to drive both ends of this system. Because of the nature of dielectrics and the value of dielectric of air and the typical value of dielectric of fuel, normally when it's full of fuel you'll get 1 nanofarad for the size of the plates that we've used, and when it's just full of air this will change to half a nanofarad. So we're looking for a reasonable change, but we end up with the specification for our measuring system that the customer has given us as well. So the specification is that we, out of all this system, we want a DC output accurate to 2% or less than 500 microvolts, whichever is greater. And the reason why this is an important definition, will become apparent a bit later. You might say, well, why have two definitions when one will do? But the percentage one is quite tricky to achieve for very low variations, because 2% of a very, very small value is a much smaller value. So that's saying the absolute accuracy has to be absolutely phenomenally huge. And at low values, we're not that interested really. So 500 millivolts tolerance at the bottom end from microvolts is fine for our system. A transient response time of less than 0.2 seconds. So that means if suddenly a bubble of air whizzes through this sensor, it needs to respond within 0.2 of a second to its full value. So what we're really saying is that the maximum time a bubble will take to go through here is 0.2 of a second, and we need to have seen it and responded accurately by that time. So they're the main sort of accuracy specifications that we're going to be working to. And we said it's going to be a differential type measurement, and one of the methods we can use is because it's capacitance, is to use alternate phase drive to each capacitor, which means that this one is going positive sine wave, so that we've got a sine wave on at this point here going up and down like that, and this one we've just got the same sine wave but opposite in phase, 180 degrees out of phase. So when this one goes up, this one is going down and then up, and this one goes up and then down. So they're sort of in alternate phase opposition to each other, and we would then sum the response at this junction and use superposition to work out what's going on. If everything's equally balanced and you sum a sine wave that's going up and then down with one that's identical except it's going down then up, you end up with nothing here. Everything cancels out. But as soon as these capacitors go out of balance with each other, you end up with a residual sine wave here, whose amplitude is proportional to the difference in the capacitances here. And that is a good time to stop, and we'll pick that up on Thursday, isn't it? I think, or Friday. Anyway, the next lecture, and we'll go into how we solve this problem, how we build an instrumentation system to meet this specification, how we test it, and where the problems may lie. It's not as easy as you think, but it's quite an interesting exercise. Okay, so we stop there. Thank you very much, and I apologise for dropping out in the middle, but it wasn't my fault. And I hope that you got something from that. So, see you next time.